Alrighty, so here we are at example 2. In example 2, we're going to see something extremely similar to what we saw in example 1, and hopefully we'll be able to see that they've given us a bunch of clues that we can use to do the shortcut method of this rather than the long, difficult way of doing this. So first of all, I have got myself a weak acid here, and then I've got a strong base here. So now my weak acid, what I've got is I've got 50/100ths of 0.5 molarity, so that's obviously going to be 0.25 molarity. And for my strong base, I've got, again, 50/100ths of 0.5 molarity, and that is going to be equal to, again, 0.25 molarity. So I am at the equivalence point, and I know I'm at the equivalence point because I have the same amount of acid and the same amount of base that are here, and so I have reached the equivalence point. Now, based upon the last problem that we just saw, you are going to be presented with a certain equation, and you're not going to want to do it that way. You're going to want to pull the reversified flim-flam version of it and do the backwards way. So the way as presented to you is you're going to take the HClO, which is hypochlorous acid, which is a weak acid, and react it with the OH negative that's there. I'm ignoring the potassium because it's going to be a spectator. And I'm going to get out of it water and the hypochlorite ion over here. If you see water on the right-hand side over here, you know you don't want to do math with this equation. This is going to not end well for you in a variety of different ways. None of the math that we are going to do is going to require water as a product. Everything for Ka and Kb, which is ultimately what we're trying to do with all of these, is going to have water on the left-hand side of the equation. So if I were to do this I, C, and E and recognize that this is 0.25 and 0.25 and nothing and 0, I'm going to take this all the way to be left with none, none, and 0.25 over here. Oh, right, I see. So I'm going to take it all the way, and now what I'm going to do is I am going to reversify it and flim-flam it. So by reversing it, I'm going to put these over on the left-hand side. So I'm going to start with ClO negative plus water is going to come over here to form OH negative plus HClO. And I've got an I and a C and an E here with my 0.25, 0, and 0. And what I need now is I need a K for this. Don't forget, you were given Ka of your acid, that's here, 3.5 times 10 to the negative 8th, but you don't have Ka now. This is Kb. So this is the basic version of the system. So you're going to have to take 1 times 10 to the negative 14th and divide it by 3.5 times 10 to the negative 8th. So 1 times 10 to the negative 14th divided by 3.5 times 10 to the negative 8th. And I'm going to end up with a K value here of 2.86 times 10 to the negative 1, 2, 3, 4, 5, 6, 7th. 286 times 10 to the negative 7th. So now what's going to happen is I'm going to do a minus x plus x plus x just like we did before, 0.25 minus x. If you'd like to, you can keep the x, do it the long way. I'm not going to. I'm going to get rid of it because my K value is extremely small. So I'm going to cheat and get rid of this guy here so that I'm going to end up with x squared over 0.25 is equal to 286 times 10 to the negative 7th. So I'm going to take that and I'm going to multiply it by 0.25, and then I am going to square root that answer, and I'm going to end up with an x value of 2.67 times 10 to the negative 1, 2, 3, 4th. That's here. And remember, x is my OH that's here. So in my pH square, where I have H positive, OH negative, pH and POH, this is 267 times 10 to the negative 4th. I'm going to go ahead and logify that, so log that answer, and I end up with a 357 for my POH, and then add that to 14, and I end up with a 1043 for my overall pH, which again makes sense because it's in the basic zone. And if it is in the basic zone, the base should be stronger than the acid, and it is, because remember up here they gave you a strong base and a weak acid that's there. So if you can recognize that you have a strong weak system that is at the equivalence point, you dilute it, you take it all the way over to the right, you flip it, and you end up doing a normal conjugate problem of what it was that was presented to you. It was presented to me as a weak acid problem because they gave me Ka. But because they are reacting a weak Ka against a strong base, it's going to ultimately end up being a Kb problem of the diluted conjugate base once it has reached the equivalence point. One more here. Example 3. Example 3 is going to be the same thing, except it's going to be in the opposite direction. Can you recognize that? We've got a weak base that's given to us here. So you think this is going to be a Kb problem, but nope, it's going to turn out to be a Ka problem. How do I know? Because I'm doing a weak base that's here with a strong acid that's here, and I'm going to do it at the equivalence point. How do I know it's at the equivalence point? Well, let's check it out. 25 and 50 is going to be 25/75 of 0.6 molarity of my ammonia, which is my weak base. So 25/75, it's going to be a third of 0.6. That's going to be 0.2 molarity of my weak base. And then I'm going to have 50/75 of 0.3 molarity of my hydrochloric acid, which is my strong acid, which again is going to be H3O positive that's here, because again that is going to be my strong acid. So that's going to be 0.2 molarity of my strong acid. So do you recognize that they are at the equivalence point? Now they did a lot to hide that from you in this process. They did a whole lot to hide that from you. They gave you weird numbers that weren't the same concentrations, and you had to dilute them and put them together. But this is the equivalence point of a weak base and a strong acid. Now, as presented to you, this is ammonia plus H3O positive is going to come over here to form H2O plus the ammonium ion. You should recognize that you don't want to do math with this because water is on the product's side. So as presented to you, this problem is terrible and frightening and awful, and you don't want to have anything to do with it. So what are we going to do? Well, we're not going to play their game. We're going to take it all the way, we're going to flip it, and we're going to turn it around, and we're going to go back in the other direction. So I've got an I, I got a C, and I got an E. I got a 0.2, and I got a 0.2, and I got a who cares, and I got a nothing. I'm going to take it all the way because water is on the right-hand side, and I know it's essentially going to go 99% of the way over to the right-hand side. So that I'm left with none and 0.2 over here. Now, I'm going to flip it backwards. And I'm going to do NH4 plus water is going to come over here to form H3O positive and NH3. And I got an I, I got a C, and I got an E. And I'm going to start with 0.2, 0, and 0, which were my ending points. I'm just going to restart those there, except that they are now backwards. On the right was left, the left was right. Why do I want to do this? Because check it out. This is the Ka format. This is a conjugate acid plus water is going to go to the H3O positive and the conjugate base over here. So you are going to end up with the Ka of NH4 positive, except that they did not give you the Ka of NH4 positive. They gave you the Kb of NH3. But by giving you the Kb of NH3, they have actually given you the Ka of NH4 positive. So the Ka is going to be equal to 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th, which is 556 times 10 to the negative 10th. And so this is going to be a minus x and a plus x and a plus x situation to be 0.2 minus x, x, and x. If you want to, you can get rid of this because my k value is extremely small. And so you're going to end up then with x squared over 0.2 is equal to 556 times 10 to the negative 10th. And you're going to go through and you're going to solve for x. So 556 times 10 to the negative 10th times 0.2, and then square root that guy. that gets you an x value of 1.05 times 10 to the negative 1, 2, 3, 4, 1, 2, 3, 4 fifth, which makes sense. And then that x is this guy here, which is your H3O positive. So we basically almost don't even need to do the pH square at that point, because this is H3O positive, OH negative, pH and POH. You've got 1.05 times 10 to the negative fifth. You barely even need to go around the square, because all you got to do is take the negative log of it and you're done. So log that guy. And I'm going to end up with a pH of about 497 in this particular case. So guys, I know this is complicated, but this is one of those things where the puzzle and the riddle of this is actually quite easy once you recognize the game that you are being asked to play. And if you are being asked to play a strong weak at the equivalence point, like we have here, a strong weak at the equivalence point is going to end up being a diluted conjugate problem of the opposite of the conjugate weak system. So if they give you a weak acid, you're going to end up diluting it and doing a simple Kb problem. If they give you a weak base, then you're going to end up diluting it when you mix them together, and you're going to end up doing a simple Ka problem because of the way that these guys work out.